Hello everyone, my name is Marcelo Castro and I am going to present the paper entitled Experiences with Dynamic Mode Decomposition for Wide Area Mode Estimation. And this paper was co-authored by Luigi Vanfretti, Chetan Mishra, Xin Zhu, and Kevin Jones for the 10th workshop on modeling and simulation of cyber-physical energy systems in May 2022. So well, as a little bit of a background, the synchrophasor technology was first proposed and tested in the 1980s and became widely deployed after government projects that bolstered the deployment of the technology. The principle is simple. A device measures the voltage and current, and with GPS synchronization, it is possible to have a timestamp associated with the measurement. This allows for the calculation of phasors that are synchronized throughout the different measurement devices uh, spread out throughout the system. And this is extremely important in the context where measurement data is needed to support the ongoing transformation of electric power grids into cyber-physical systems. So these phasorial measurement units, or PMUs, are installed in substations and have recently been applied to different applications related to the monitoring of power system oscillation, especially the wide area oscillations, which consist of low frequency modes. One of such techniques is the DMD, the dynamic mode decomposition. And in order to calculate wide area modes that are found in power systems, it is necessary to understand modal analysis. So modal analysis is a study in which it assumes that under small perturbations, it is possible to approximate the power system's nonlinear dynamics to a nearly linear behavior. So with that, it is possible to extract eigenvalues that are characterized by mode frequency and damping. And in this linear analysis, it is also possible to extract eigenvectors, which tell us a lot about the composition of the original signal, and it unravels the mode shape and tell us if machines in that power grid are actually swinging together or against each other in a particular oscillation. So dynamical mode decomposition is a technique first proposed in fluid dynamics that allow us to use multi-channel data in order to perform modal analysis, such as the one described previously. It is extremely useful when there is a large number of measurements with small number of governing dynamic patterns. This is good because this is exactly the case for wide area modes which are observed in power systems. So the technique is based on the selection of measurement streams, which are then organized into a series of vectors composing a matrix X at time step K, and another matrix X at time step K plus 1. So by using a best fit linear operator and leveraging singular value decomposition, it is possible to perform a regression in order to find an approximate state matrix A. And this matrix A will tell a lot about the mode frequency, damping, together with the mode shape associated to it. So in this paper, however, we adopt a variation of the DMD technique called higher order DMD, or HODMD, which we organize in which we organize the streams into vectors with embedded time delays. This allows us to increase the apparent number of measurement streams, creating time redundancy that reduces ill-conditioned data matrices. In this particular format, two parameters need to be set now: the time delay number, which means how many time redundancy we are going to include in our data matrix, and the SVD order that will allow us to select how to compress the data before performing the modal analysis. In order to assess the HODMD technique, we are going to use real-world frequency data coming from 9 different substations in Dominion Energy's power system. The data comes from July 23rd, 2019 at 8 p.m. I mean, the data that you see in the plots. But we actually have used randomly sampled data to conduct Monte Carlo analysis in the study as well. So the data also needed to be processed prior the analysis, including the filtering of frequencies outside the interval of 0.1 and 0.5 hertz, and the resampling of the data. We also used Welch method for calculating the power spectral density, or PSD, which takes into account 2-minute long data windows with 50% overlap. And by doing such analysis, the data displayed on the right upper part of the slide is used to obtain the PSD, which is shown in the lower right corner, highlighting 3 modes. As you can see, there is one highlight centered at 0.13, one at 0.19, and another one at 0.34 hertz. By comparing the 8th order Yule-Walker technique, which are the de facto single channel approach in industry, to this application of HODMD technique to a single channel data stream, we can actually draw 3 different plots to compare the results. So figure 1 on the upper right corner shows the results for when we vary both the number of time delays and the SVD order. For instance, we see 6 delays and 6th order in green, 8 delays and 8th order in red, and 10 delays and 10th order in purple. Also, notice that the red curve and the Yule-Walker presented in orange, they show similar peaks at similar locations. So figure 2 on the lower left corner of the slide shows the result when we fix the SVD to the 8th order and vary the number of delays to 10, 14, and 18. Note that with the fixed SVD order, the higher the number of delays, the higher is the steepness of the peak identified. This means that a high number of time delays can hinder the damping estimate. Figure 3 on the lower right corner of the slide shows the result when we fix the number of delays into 10 and vary the SVD order. Note that the number of identified peaks is directly influenced by the SVD order, meaning that it is quite analogous to the Yule-Walker model's order. So since HODMD is a multi-channel approach, we leverage this by analyzing the data from all substations at once. And to do so, we set 7 time delays and impose an SVD order of 22. And the result of the PSD is seen in the lower right figure. We then proceed to perform a Monte Carlo analysis in which the data is randomly sampled at different dates, and the result from this analysis is shown in the table located at the top right corner of the slide. Notice that we have also compared with a single channel Yule-Walker estimate. And since HODMD is a multi-channel approach, it is expected to observe a higher variance in the estimate, which is confirmed by the data on the table. However, it is also important to note that the frequency and damping estimates are comparable between these 2 techniques. Another benefit of using DMD-based techniques is that we directly have access to mode shapes, which should be calculated separately when using other techniques such as your Walker methods. Here, we use cross-spectral density method to estimate the mode shape, and as one can observe, the results are similar to the ones obtained with the HODMD. Although CSD estimates, the estimated shape, seem more scattered, especially in the mode at 0.3067 Hertz, it still represents a set of coherent generators, which is also shown in the DMD-based approach. Finally, to conclude this work, we can highlight mainly 3 points. The first is that we briefly described and presented a DMD-based method and how these methods can be leveraged in the context of power system applications with PMUs. Second is that we made comparisons between HODMD and Yule-Walker to better understand the method and how they can be analogous in different terms. By choosing appropriate parameters, both methods identified similar frequencies and damping ratios for a large number of data. And although HODMD-based techniques presented in this estimation are not single channel. They use a multi-channel data stream set, which is much more efficient method than the single channel Yule-Walker approach. Third point that should be noted is that the DMD-based techniques also allowed us to analyze the properties of the mode shape without any additional calculation. And this is really useful when using data to tune controllers and mitigate effects of wide area oscillations, or even to identify sources of oscillations when we are doing this kind of studies. So this is a very interesting benefit from using DMD-based methods instead of other techniques. So therefore, we can conclude that DMD techniques can be extremely useful in the future power systems, especially considering the context in which data is going to be much more relevant. And as future works, we can point out that more study is needed when data points are missing from the streams and in the derivation of data-driven models from PMU measurements, which are used in the study. Finally, we would like to express our gratitude to Dominion Energy for supporting and sponsoring this work. And thank you so much for hearing to this presentation. And should you have any questions, please feel free to reach out to me at the email address listed in the slide. Thank you.